All right, so this talk is based on a paper from last December, which is up at ABGM, as well as a review of some earlier work on n=4 super-Yang mills. So the motivation is to understand non-perturbative string theory. So the only non-perturbative definition of string theory that we have at the moment is from holography. So the classic examples of that are type 2b string theory on 85 crosses 5, which we know is dual to n=4 super-Yang mills. In that instance of the duality, you have the string length and the complexified string coupling, which is related to the CFT parameters, as shown here. So you have the complexified gauge coupling is just identified with the complexified string coupling, and then you have the ratio of the ADS radius and the string length is related to the tuft coupling. The other classic example of ADS CFT relates M theory in ADS4 crosses 7 mod ZK to a certain 3D CFT called ABGM, which is this Chern-Simons matter theory with two gauge groups. And so in that duality, on the string side, you only have one parameter because this is M theory, so you don't have a string coupling. You just have string length, or more accurately Planck length in 11 dimensions, which is then related to the CFT parameters K and N by an analogous relation. So the fundamental entry to this duality, which we're going to be discussing today, is that graviton scattering in the quantum gravity side in ADS is dual to a correlator in the CFT of the stress tensor multiplet. So the idea of bootstrapping holography is as follows. So ADS CFT back in the 90s recast quantum gravity, at least in the context of ADS, into the easier problem of CFT. But it only kind of half solved the problem because the CFTs that are dual to quantum gravity in ADS are strongly coupled. And so they still can't actually be studied in practice. So some people might naively sometimes think that ADS CFT somehow solved quantum gravity in ADS, but it's just not true. It just translated it to CFT, which is also an unsolved problem, strongly coupled CFT. So in certain limits, there is some control on these strongly coupled CFTs. So for instance, if you look in the Plater limit large N, which in the string theory side is the classical string, then there's this method called integrability, which could be used to study quantities at finite tuft coupling. But this is all just the classical string. This doesn't give us any insight on the quantum string, and it certainly doesn't give us any insight on M theory, because there is no weakly coupled string limit in that case. For the specific holographic dual involving super-Yang mills, in that case, that CFT does have a weak coupling limit, as any 4D gauge theory would, but that's the opposite limit of what we would care about if we care about gravity. Because the gravity limit is when you're at large N and strong coupling, and that's the opposite of this weak coupling limit. So doing weak coupling on the field theory side only really tells us about the super stringy regime, which can still be interesting, as Nathan has worked on, but not if you're interested in Einstein gravity and corrections. So today, we're going to combine 3 non-perturbative constraints to numerically study holographic CFTs and thus quantum gravity. So in particular, these 3 constraints, the first one is unitarity, which in the context of this talk will be the fact that OP coefficients must be real and the scaling dimensions of operators must be bounded. The second constraint is crossing symmetry, which could be combined with unitarity in order to formulate the numerical bootstrap algorithm, which is what the other conference, of which this talk is not a part of, is about. And the third non-perturbative constraint is supersymmetric localization, which allows us to input protected coupling-dependent quantities into the bootstrap. So as far as I know, these are the only 3 completely non-perturbative constraints that we are aware of in the context of correlation functions in CFTs. So we're kind of putting in everything we possibly can in order to non-perturbatively study the theory. Okay, so let's first begin by discussing n=4 super-Yang mills. So all n=4 CFTs have an SU4R symmetry and are conformal manifolds with one complex parameter tau. And so you can define these theories by specifying their central charge C, which in the case of a gauge theory would be the dimension of the gauge group divided by 4, and also by specifying the complex coupling tau. And so this is just on general grounds, without knowing anything about the theory. The only known n=4 CFT, though, in 4 dimensions, is n=4 super-Yang mills, which is a specific gauge theory where the matter transforms in the adjoint of the gauge group G, and it must be a compact classical Lie group. And so for this talk, we're going to deal with the case where the Lie group is SUN, in which case C is n squared minus 1 over 4. But pretty much everything we do in this talk could very easily be generalized to other Lie groups, like SON or exceptional groups, what have you. So n equals 4 superring mills is in fact a conformal manifold. It's not just a single CFT. And so like any conformal manifold, there's something called a duality group, which relates different points on this manifold, i.e. it's relating different CFTs. And so in this context, the duality group is SL2Z. There are two special points along this conformal manifold. One is a self-dual point when tau equals I, in which case you have an enhanced global symmetry of Z2, and the other case is when tau equals e to the I pi over 3, in which case there's an enhanced symmetry of Z3. So the quantity we're studying is the stress tensor correlator, and in general, in the Bootstrap, we expand the stress tensor correlator in conformal blocks, which is done just by taking the OPE of the, the two pairs of operators in the 4-point function. So in this specific correlator, there are two kinds of multiplets that appear. The first kind are protected multiplets, which we write by this term. These are trivial in the sense that their OP coefficients do not depend on the coupling lambda. And the way they depend on C is also very simple. They're just linear in 1 over C. So that means that in particular, you can compute all the CFD data of these protected terms from a free theory, and that's why they're kind of trivial. And so we don't really care about them so much. The next term in the block expansion is this one, and this term is referring to long multiplets, which can have unfixed scaling dimension as well as unfixed OP coefficient lambda. And supersymmetry is automatically satisfied as long as you have this kinetic term here, which is fixed by symmetry. And so the goal in studying this 4-point function is basically to study the scaling dimensions and OP coefficients of these long multiplets, because that's the only non-trivial content of this 4-point function. So the first non-perturbative constraint we consider is the cross-theory equations, which, as usual, when you consider a CFT in Euclidean space, comes from swapping the 4 operators that appear in the correlator. In particular, if you swap the first and the third, then you know the left-hand side must be invariant, but the right-hand side must change. And demanding that it doesn't change gives you a function's worth of constraints on the scaling dimensions and OP coefficients according to the usual Bootstrap algorithm. So this algorithm was first formulated by these authors back in 2013. And they used it to get upper bounds on the scaling dimensions of these long multiplets, as well as the OP coefficients for every even spin as a function of C. Because they could input C, because C appears explicitly in these protected terms. So you know the exact function of C here. On the other hand, they could not input the value of tau because there was no quantity they knew as an exact function of tau. And so that was a limitation of the study from 10 years ago. So before we talk about the new non-perturbative results, we can review some perturbative data. So first of all, we have the weak coupling expansion when G mills is small. Alternatively, you could think of it as the tough coupling being small. In this case, you can just compute quantities using Feynman diagrams as you would in any 4D gauge theory at weak coupling. And so for instance, for the lowest spin unprotected multiplet, which at weak coupling is called the Konishi, there's been a series of many works over the years, culminating in this paper by Velejanin in 2009, where they computed the scaling dimension to 4-loop order. And so one kind of curious fact here is that the first non-planar correction occurs at 4-loop order. At the previous loops, it's just totally planar. But this is finite n, because you're doing weak coupling. And you could similarly compute OP coefficients to the same order. This was also done, contributions from many different authors, culminating in the 4-loop result by these authors in 2020. Another perturbative method is integrability. So this method is perturbative in n instead of being perturbative in G-mills. And so in the strict large n limit, called the planar limit, you could compute quantities for finite lambda. So for any value of the coupling times n. And so the most advanced formulation of integrability is called the quantum spectral curve, for which we heard, I think, a review talk last week. So this was done back in 2014. And even though it was first formulated in 2014, it's actually very hard to numerically solve this quantum spectral curve. And so it was only basically 10 years later, i.e. last year, that they were able to really efficiently extract the entire spectrum from the quantum spectral curve. And so they know, all the single trace operator CFT data, at least for scaling dimensions, in the planar limit. So there's a couple checks on their results. So one such check is that if you look at the results at small lambda, that matches weak coupling from the previous slide. And then at large lambda, there's also some predictions from string theory, from some classical string solutions, that the scaling dimension of the Konishi should go like lambda to the quarter with this specific factor of 2, and then a minus 2, and 2 over lambda to the quarter. And all these predictions from string theory were matched by integrability. which is a very nice check on that method. And so notice that the Konishi operator gets very big at strong coupling. So whereas it was very light at weak coupling, it's huge at strong coupling. So integrability is a very powerful method, but its limitation is that it's only really understood in the Plater limit, and so it's only telling us about the classical string theory, which means like leading string coupling. And so one manifestation of this limitation is that higher trace operators are just trivial products of single traces. So for instance, the lowest double trace operator is just a product of two of the stress tensor multiplets, and so in the planar limit, its scaling dimension is just 2 + 2 = 4. And so you're not sensitive at all to the first non-trivial correction, which is at order 1/n², which is beyond the planar limit. Okay, so now we're going to talk about a question. Yeah.
Yeah. So a priori, this kind of perturb calculation, let's say, is subject to a scheme ambiguity, right? That you can imagine different schemes differ by a redefinition of the coupling. Of course, in practice, well, I mean, the integrability scheme somehow coincides with localization, but is it clear that, let's say, the non-planar computation perturbation theory would necessarily coincide with the same scheme as using localization?
I mean, people have done some comparisons between localization and weak coupling in some examples. And I think there's even examples beyond the planar limit. Like I think Arkady and Zeitlin and others did such calculations.
I mean, in fact, as far as I know, maybe someone can correct me, but as far as I know, usually the perturb computation is done with a dimension reduction scheme, which is known to be inconsistent, because after Warren Siegel's original paper, a year later, he wrote a paper to say that it's actually mathematically inconsistent, but people never encountered issues up to, let's say, for loop order, but in principle, you could imagine that at some point you run into trouble.
Yeah, I mean, it could be. Yeah, I mean, I know people have certainly done many calculations, I think with like Wilson loop expectation values. I don't know if they went beyond the planar limit. Maybe. Yeah, but this is an interesting point though, yeah. So like it could be the weak coupling expansion itself doesn't really make sense at some order. Anyways, so now we're going to talk about non-perturbative constraints. We've already talked about crossing symmetry and unitarity. So the last non-perturbative constraint is localization. And so the idea here is that you have the sphere free energy of the theory deformed by a mass, where m is the mass of a hypermultiplet. And so if you take derivatives of the sphere free energy as a function of mass, then because the mass couples to the stress tensor multiplet, after you set the mass to 0, it gives integrated constraints on the 4-point function. So if you're considering just the 4-point function, in principle you could take more derivatives to get higher point functions. There are two independent constraints, which we now know for a fact. And so they take the following form. So in one case you take 4 derivatives of mass, in another case you take 2 derivatives of the mass and 2 derivatives of tau, where tau also couples to the stress tensor multiplet. And it equals just specific integrals of the 4-point function, which here we've written in its block expansion form, so as to relate to the previous slides where we also discussed the block expansion. So this I2 and I4 are specific integrals, which are given in the paper. They're not so important for this purpose, but the point is that we know them exactly because they're just fixed by symmetry. Now, the reason why it's interesting to have such a relation is that in the supersymmetric theory, you can compute this f of m non-perturbatively, which was shown by Pestun 15 years ago. So in particular, you can simplify the infinite dimensional path integral into a finite dimensional matrix model integral, as shown here. So these h's are certain special functions. You see the coupling appears over here in this classical term. And then there's an instanton term, which is where all the theta angle dependence comes from. This instanton term is extremely complicated, but it was computed by Nekrasov and is known in closed form. So it's some kind of infinite sum for every single instanton sector. And so with this expression, in principle, you know this quantity non-perturbatively, although you have to do n-1 integrals. So for low n, you could just do these integrals numerically and take the derivatives in mass, and that would give you the input you would need to combine with the bootstrap. But ultimately, we're interested in bigger values of n because that's the gravity regime. And so if we want to look at bigger values of n, we need some more efficient methods because you can't just take, say, like 20 integrals numerically. So if you ignore instantons in the previous slide expression, then it turns out that you can actually compute these mass derivatives exactly using the method of orthogonal polynomials. Now, the reason why this is possible is that the matrix model for n equals 4 super Yang-Mills when the mass is 0 is just a free matrix model. It's the simplest thing. And so you could compute any observable in a Gaussian matrix model. And so when you take derivatives of mass set mass to 0, you're just computing complicated observables in a free theory. And so that's why it makes sense that a method should exist to give you the answer. And so this was done in this paper I had from a few years ago. And for the two mass derivative case, this is the answer you get. So as you see, you have simplified n-1 integrals into a single integral in terms of this auxiliary variable w, where these L's are Laguerre polynomials, and there's just a single finite sum up to n. A complementary approach, which does take into account instantons, is that you can study this observable in a large N expansion using various matrix model tricks that we developed a few years ago, and you find that the answer is written in terms of some known non-holomorphic functions. So for instance, for the two mass derivative case, to every order in 1 over n, it's written in terms of these non-holomorphic Eisenstein series, which kind of famously show up in the string theory S matrix in flat space. And so this is giving the complete answer, including all instantons, but only in a 1 over n expansion, although we can go to any order we want. And there's a similar expression for the 4 mass derivative case, which now includes another class of modular functions called generalized Eisensteins, which is our not very creative name for the other functions that appear. So the novelty of this paper from a year and a half ago is that we figured out a method of combining this large N and including instantons with finite n but no instantons in order to get an accurate approximation to these observables for every value of n, including instantons, which is what we need for practical implementation with the Bootstrap. And I should say that this whole program was inspired by a wonderful paper by Jorge Russo, which came out, I guess, roughly 20 years ago, first studying these matrix models in the large N expansion. Okay. So before we talk about our non-perturbative results, we can talk about one final perturbative limit. So far we've done weak coupling using Feynman diagrams, and we've done integrability and the planar limit. There's one last limit, which comes from ADS-CFT itself, which is the strong coupling limit. So you can use the principles of crossing symmetry as well as analyticity in order to fix the large N expansion, which you could also think of as the large C expansion, of this 4-point function in terms of a finite number of coefficients at every order in 1 over C.
Can I ask a question?
Yes.
Are there independent checks of that instanton contribution apart from SL2Z duality?
You say the check of Nekrasov's calculation?
Yes. Let's say.
Yeah, I mean, yeah, so numerically you can check that it satisfies SL2Z. So that's, I guess that's one check.
Is that the only check?
Maybe.
Because these things, as far as I understand, typically involve singular instantons. I'm not sure if they...
Yeah. So indeed, okay, so Nekrasov's calculation is more subtle than people might be aware, because there's other examples of 4D n equals 2 theories, but actually gives the wrong answer. So for n equals 4 Spring-Mills in particular, we believe it gives the right answer. Okay, so one reason is checking SL2Z numerically. Another reason, which I'm about to talk about, is that you can fix some of these coefficients in the correlator and then take a flat space limit and then compare it to the known type 2BS matrix where you know the answer in terms of non-holomorphic Eisenstein series and you get the same ones. So that's another check, I would say.
I guess you're saying that that's actually an independent check.
Yeah, so that's independent. Finally, I mean, maybe AGT is considered a check, you know, for false or small rank. Although, yeah, I mean, I haven't thought about that so much.
Isomorphisms tend to work out at small gauge groups, so SO6, SU4, these
isomorphisms when taking into account the instantons.
Yeah.
Yeah, sure. Yeah. I guess that would be another check if you consider these other families. Yeah, but indeed, in other cases, it is much more subtle, as Connor knows well. Anyways, so in this large N limit, so we have the correlator expanded, and we have certain coefficients we have to fix at every order, which are not fixed by these constraints. These are the constraints that are called the analytic bootstrap. So these B's are not fixed by those constraints. And so the first order is fixed. This is, in the bulk, what corresponds to tree-level supergravity. So this was fixed by Leonardo and Sheenan back in 2017. But once you go beyond leading order, there's always a few numbers you have to fix at every order. So for instance, this is the one loop term, this is the d to the 4r to the 4 correction, this is the r to the 4 correction, etc. These are all higher derivative corrections to the supergravity approximation to this correlator in the bulk. And so, yeah, so this is kind of like another perturbative limit we can compare to. Now you can use the two localization constraints I just discussed to fix two of these coefficients at every order in 1 over c. And so that is sufficient to completely fix the r to the 4 term and the d to the 4r to the 4 term as well as the one loop term. So that means in particular, we can analytically fix this correlator up to c to the minus 9/4. And then you could extract all the CFT data you want, and so you get these answers, which unsurprisingly are written in terms of non-holomorphic Eisenstein series, because after all, that's what appeared in the localization constraint. And so this kind of, somewhat relates to what she was asking, is that you can check that the correlator fixed in terms of these Eisensteins when you take the flat space limit matches the expectation, which was also fixed in terms of the same Eisensteins earlier. Anyways, so this is the lowest dimension operator in the strong coupling limit, which is the double trace operator. So this starts at 4, and its first correction is non-planar, because recall that the Konishi in this limit is going off to infinity, so it becomes very heavy. So the lightest operator is now this double trace. Furthermore, if you actually use the flat space limit, you can have one more constraint. You can get d to the 6 r to the 4. But starting at d to the 8 r to the 4, that correction is unprotected. And so that's why it's kind of conceptually the most interesting. Because you don't expect to be able to compute an unprotected correction using purely protected inputs, such as localization. So if you want to get d to the 8 r to the 4 or higher corrections, you will need something more powerful than just analytic bootstrap and localization. So just to recap, what constraints have we used so far? So for analytic bootstrap, you've used crossing symmetry, and we've also added localization. But we haven't used unitarity. And the reason why is that unitarity is trivial in the strict large N limit. Because in the strict large N limit, your OP coefficients are just trivially positive, and then corrections can't possibly change that. And so in order to get better constraints, we need to go to finite N in order to take advantage of unitarity, which means that we now have to do the numerical bootstrap. So that's kind of the main motivation of going to finite N if your ultimate goal is to study big values of N, is that you want to be able to access unitarity. Okay, so with all that behind us, we can now move on to the results. So this is our first non-perturbative result. So this is for N equals 2. And so in this plot, the x-axis is the coupling, G.A.Mills. It starts from the free theory, it goes to the strong coupling point. The y-axis is the value of the lowest dimension operator, which would be the Konishi in the Twee coupling regime. And so we can compute upper bounds on this quantity. And on the right-hand plot, we focus on the strong coupling regime, going from this one self-dual point to another self-dual point. In this plot, we don't even talk about the theta angle, because the effect of the theta angle is so small, because instantons are very suppressed. Whereas in this plot, we do show the effect of the theta angle, which, as you see, is very small from this y-axis. So the first success of this plot, which is already from a few years ago, is that if we compare it to the weak coupling estimates, we find that those estimates approximately saturate this upper bound, which gives us some evidence that at least in that regime, this upper bound is corresponding to the physical theory, which oftentimes is the case in bootstrap studies. Another interesting thing we learned from this plot is that this gray horizontal line is not a function of the coupling, and that is the bound if you didn't input the localization constraint. So this is the bound from Rosselli et al. From 10 years ago.
Wait,
Yeah.
you're calling the right plot the theta angle, but I thought you're fixing absolute value of tau, not tau 2.
We say over here?
Yeah, isn't that way?
Well, I mean, it's depending on some combination of the theta angle and G.A.Mills.
Yeah, but it's not like you're detecting the instanton contribution because
No,
you're
we are.
also varying the GM-Mills.
No, sure. I mean, but it's still, but it's sensitive to instantons. I mean,
Obviously you cannot tell whether the contribution. Correct.
okay. I guess it's a good point. Yeah. So if you really want to know, yeah.
Thought it's the one with fixed tau 2, no?
Yeah, I mean, the main thing I'm just trying to say is the effective instantons are very small. But the fact that this thing is sinusoidal, that's coming from the instantons. Because if you look at the instanton contribution, it always comes with this factor of like e to the I pi tau. And so that's the thing which is kind of fluctuating in the sinusoidal way. Although, of course, it depends on the whole tau, not just specifically theta angle. So another interesting thing we learned from this plot is that if you compare it to Rosselli's old bounds, which didn't involve localization, you see that those old bounds are not saturated for any value of G Yang-Mills. And so that basically proves that those old bounds were not related to N equals 4 super Yang-Mills. Back in the day, people thought they might have been related for some special value of G Yang-Mills. Now we know they aren't. You might instead ask, well, what is related to those old bounds? So I had this paper with Fernando Alday a couple years ago where we showed that something called pure ADS5 supergravity seems to be the thing that is saturating these bounds where you don't input localization. But I won't go into detail because that's a little bit away from the focus of this talk. So you can similarly compute bounds on the OP coefficient of this Konishi operator. So here on the left-hand side, again, we focus on like the recoupling regime all the way up to the strong coupling point. You see the bound is much more non-trivial. It's non-monotonic now. You could compare to weak coupling, and you also find a match in the weak coupling regime, although the weak coupling regime seems to be not as effective as for the scaling dimension. So we also have this result. So now we can go beyond n equals 2. So this is a result that talks about many different values of n, and now the x-axis...
Sorry, just to understand the conclusion from the previous plots,
Yes.
I mean, these are upper bounds?
These are all upper bounds, yes.
And do you expect it to be?
Yeah, so the conjecture would be that the physical theory saturates the bound, and that evidence comes from the weak coupling regime where you can compare to weak coupling. But in principle, the theory could be anywhere within the allowed region.
Have you tried to make a direct comparison with, say, the one incident contribution?
We did, but it was way too small to see any effect.
You mean there's not enough numerical sensitivity?
Yes.
I see.
Yeah, so people have computed the one instant correction at weak coupling, but that effect is just so tiny that you can't see it. Okay, so now we're looking at many different values of n. So we've rescaled the x-axis by n, so this is like the tough coupling now. And so these are just bounds on the scaling dimension for different values of n. So they start at the bottom and they go up. And so here we compare it to integrability, because when n gets big enough, integrability should be valid. And so this black dotted line is the integrability result. And you see very nicely that as n gets bigger, our upper bound starts to coincide with the integrability result. Notice that when the integrability result hits 4, it just gets stuck at 4. Because then the lowest dimension operator is just this double trace, which is just trivially 4 in the planar limit instead of being the Konishi. So this kind of shows some match with integrability. You can have a similar plot for the OP coefficient. Now the plot is starting at the top and going down as n gets bigger. It always shows the same kind of non-trivial behavior. In this case, integrability has not yet computed this OP coefficient. Well, actually, recently it did due to the work of Frank Coronado. But from what I understand from talking to Frank, I guess they weren't able to make a comparison yet within this entire regime. Yeah. Well, Frank could probably answer that the best.
So would their thing saturate to your plot then? Like, does it like how you had for the dimension?
Well, if this is at finite, if this is at finite n, so this is the OP coefficient.
This is the OP coefficient, yes.
Well, if this is at finite n, I think what happens is that the operator that you follow is not a single trace, right? Like at some point,
yeah. So
it
like,
becomes a double trace.
so because we're working at finite n, and Frank's results are all about the planar limit. So we are looking. I mean, eventually we go to fairly big value of n, but so I guess in principle we would want to compare maybe this red line to your results.
Right. The largest value of n that you have will probably approximate planar supernomial. So maybe that could be. But otherwise, for smaller values of n, I think the operator is really different from condition.
Sure. Okay, so one would expect if you plot his result there as well, then it will just be just below the red line, right?
Yeah. For some reason, I thought we discussed this before, and you said there was some difficulty in doing that, but I don't remember now. Anyways, yeah, but it would be interesting to try that. Okay, so now we could focus on a specific large value of n, which is to say n equals 10, and we can again show one of these plots on the lowest dimension operator. So just as before, we find a nice match to weak coupling, which is this blue dotted line. But the nice thing is that now, because n is big, we can also compare to strong coupling. So remember, we had the strong coupling result, which was using analytic bootstrap plus localization. And so that's what this maroon dotted line is, and that also matches. And so this gives even more evidence that this upper bound is corresponding to the physical theory, because now we have evidence both from the strong coupling regime as well as from the weak coupling regime. Whereas for n equals 2, we only had the weak coupling regime. Now, the most interesting part of this plot is this little region over here where neither weak coupling nor strong coupling is a good approximation. And so that you could say is the non-perturbative regime where you really needed the numerical bootstrap, that little sliver over there. This is also kind of like a zeroth order result about level repulsion, because we know that at weak coupling, the lowest operator is single trace, whereas at strong coupling, the lowest operator is double trace. And so at some point, these things should kind of like cross over each other. And that's the kind of thing you learn from having this non-perturbative result. So this is a similar result for the OP coefficient. It's a bit more dramatic than the scaling dimension. As you see, there's a huge difference between the weak coupling regime over here and the strong coupling regime over there. So you could imagine that as n gets bigger and bigger, I suspect this plot would start to resemble a theta function, where it would just be here and then go all the way down and go like that. And that really kind of shows the rearrangement of the spectrum.
Looking at the plots, it seems that the extrapolation to lambda equals infinity can have big error bars. No?
You say, oh, okay, yeah. So that's a good question. So for the Bootstrap experts in the room, there's always this lambda parameter, which basically says how much of the crossing equations you're inputting. Because you have to always, crossing equations are some functions worth of constraint, and you're only sampling some finite amount. So as lambda gets bigger, the bounds get better and better. So indeed, in order to get these results, we had to do an extrapolation to lambda equals infinity. And the reason why we think that extrapolation works is, well, first of all, just if you look at it, it seems to work. And we did a very simple extrapolation. We just did a linear extrapolation. We didn't like do some fancy thing to get what we wanted. So we did the simplest extrapolation you could do. I'll also have a plot in the next slide where I kind of show more evidence that this extrapolation should be trusted. Okay, so this is just more values of n, just to show it's not a coincidence for n equals 10. Okay, so this addresses Shai's question. Oh, sorry, we did a polynomial ansatz. Yeah, so we included 2 terms in this whatever lambda expansion. And so this plot kind of shows like why you should believe our extrapolation. So this is just showing an example as a function of 1 over lambda for some specific value of G-ing mills and for some specific value of n. And it seems that our data indeed seems to roughly match this kind of simple polynomial ansatz. And so we use the same ansatz for every single value of G-ing mills, and in all cases it seemed to give reasonable results. But of course, indeed, that is a non-rigorous aspect of our calculation. Okay, so the last thing I'll say about n equals 4 is that if you want to compare it to stringy corrections, which is ultimately our motivation, here you could focus on large n and at strong coupling, and you could compare our upper bound here to the large n predictions from analytic bootstrap plus localization. So these are like the string theory predictions. And so here's the plot for scaling dimension as well as OP coefficient. And so you start with the leading term, green, which is horizontal because it doesn't depend on the coupling. That's the supergravity approximation. Then you include the first term, which makes it red, which is r to the 4. And then you include the next term, which is 1 loop. And as you see, as you include more terms, the analytic large n prediction gets closer and closer to this non-perturbative bound, which is an example of how we are becoming sensitive to stringy corrections. Now, of course, we're not at the level of accuracy where we can give predictions. And there's still a lot of room to go, but I think we're going in the right direction. And as you'll see in the moment for ABGM, we have much better results. Okay, so that concludes n equals 4, which was the review of results from like, a year and a half ago. Now we can go to the more recent results from last December about ABGM, which are much better. So all maximally supersymmetric 3D n equals 8 CFTs have an SO8 global symmetry due to the R symmetry. And all the known theories are these Chern-Simons matter theories with 2 gauge groups shown here. If we want to focus on maximal supersymmetry, then the Chern-Simons level can only be 1 or 2, and the difference between the gauge groups can also only be 1 or 2. And so basically there's 2 cases. There's the case where the gauge groups are the same, which we call ABGM, and there's the case where they differ by 1, which we call ABJ. One other relevant fact is that when k equals 1 and the gauge groups are the same, then the theory is actually a product theory between a free theory and an interacting theory. We only care about the interacting part. This CFT is strongly coupled in general, because k is fixed to be finite if we want maximal supersymmetry. The only exception is when n equals 1, in which case it's just a free theory. But we don't care about that. So just as in the case of n equals 4, we can label the CFT by quantity we call CT, which is the coefficient of the stress tensor 2-point function. It scales like n to the 3/2, although unlike n equals 4, it's a non-trivial function of n. So it's not just something like n squared. Okay, so we look at the stress tensor correlator just as before. Question? We again expanded in superblocks for each multiplet. These are fixed by the superconformal Ward identity, which was worked out by Dolan, Gallo, and Sokachev. The multiplets that appear are much more non-trivial than the n equals 4 case. So like the n equals 4 case, we have long multiplets, which is what we write here, which have unfixed scaling dimension and spin. But unlike n equals 4, the short multiplets are now non-trivial. They are non-trivial in the sense that their OP coefficients are a non-trivial function of k and n. So of course the scaling dimension is fixed because they're protected, but the OP coefficient is non-trivial. And this is a good thing, because the fact that we have non-trivial short multiplets, because they are separated from the continuum of long multiplets, this means according to the standard Bootstrap algorithm, we can rigorously compute both upper and lower bounds without any assumptions. So that means we can automatically get islands for these OP coefficients, which is something we could not get in n equals 4 because they were just trivial in that case. So the protected operators I'm talking about, they come in 2 classes. There's the B operators, there's 2 of them. These are what are called short operators, and then there's these A multiplets. You have 2 of them, and you have them for every even spin for A+, every odd spin for A2, unlike these Bs which only have spin 0. And these are called semi-short multiplets. And so these guys are the non-trivial ones with OP coefficients. Okay, so just as in n equals 4, in addition to cross-check symmetry and unitarity, we also have localization. And so you could deform the sphere of free energy by masses. Now there's 3 masses, unlike the 1 mass in the n equals 4 case. And it was shown in these papers that there's 2 exact constraints you can derive by taking different derivatives of different masses, as shown here. So the first integrated constraint, the integral actually trivializes. So it turns out that it just becomes an exact relation to the OP coefficient of these two short multiplets, b plus and b2, as well as the stress tensor, and the unit operator. And this is basically due to the existence of this 1D topological theory. I won't go into detail. Finally, if you take two derivatives of the mass, you could compute CT itself, which I remind you is a non-trivial function of n, unlike 4D, where it's a trivial function. Finally, one last non-perturbative constraint is that if you can use this 1D topological theory, in that theory, it only describes protected operators, so it becomes much simpler, and so you can just exactly solve crossing symmetry, and you get this relation. And so at the end of the day, you can combine this relation with that and with that in order to write all the short protected operators, which means b plus, b2, and the stress tensor. You can write all of these things in terms of mass derivatives. And then, just as in n equals 4, we use the fact that these mass derivatives could be computed using supersymmetric localization non-perturbatively in terms of n and k. So if we just consider two of the masses, which is the only cases we're considering in this talk, then the matrix model takes this simple form where everything is written in terms of cinches and coches. Turns out you can actually completely solve this matrix model. So originally the matrix model was solved to all orders in 1 over n by Mourinho and Putrov and Nosaka. And the answer was written in terms of these airy functions. But then, in the last couple of years, Nosaka went a step further, and he just solved it completely non-perturbatively. So Nosaka gave an exact result, which is finite in n, k, and m. It's finite in every parameter. So this might relate to Henry's talk earlier today about using matrix bootstrap to study matrix models. One could perhaps try to reproduce these exact non-perturbative results for this non-trivial matrix model. So the point, though, is that we have inputs completely. So unlike n equals 4, we had through some games in order to get finite n and finite tau, here we could just use Nosaka's result, straight out of his paper. Okay, so just as in n equals 4, we have these analytic bootstrap results, which allow us to fix the correlator in this large n expansion. So similar to before, we have the leading term, which is tree-level supergravity. We have higher derivative corrections. We have one loop. These were fixed in a series of papers by me as well as other people. Just as before, with n equals 4, you can use supersymmetric localization to fix some of these coefficients. So in particular, you can fix the r to the 4, the d to the 4, r to the 4, and the one loop, which in particular means you can go up to order c to the minus 19 ninths, which actually vanishes. Furthermore, because people know the flat space limit of this correlator, which is the M-theory S matrix, this was computed up to order d to the 6 r to the 4 by Michael Green and collaborators. If you trust their result, that allows you to fix one more term. So you can get up to d to the 6 r to the 4. But just as I spoke about for n equals 4, starting at d to the 8 r to the 4 correction, that's unprotected. And so there's no expectation that we should be able to fix that using purely protected quantities, and indeed that's completely unknown. And so it's one of the big questions of non-perturbative string theory to answer the question, what is d to the 8 r to the 4? So in particular, we would need 4 constraints to fix what we know from the large n expansion. So going up to d to the 6 r to the 4, which we know, you can extract all the CFD data you want. So for instance, for this A plus semi-short OP coefficient, this is the answer, up to order c to the minus 23 ninths. So the highest order is d to the 6 r to the 4, which is 7/3, shown here. And then the goal is to be able to see if we can get the higher derivative correction. So d to the 8 r to the 4, which starts at 23 ninths, according to dimensional analysis. Okay, so now let's move on to the results, which is the non-perturbative results from combining unitarity, crossing symmetry, and localization. So this plot is showing how we've improved over the years. Because in fact, the very first paper I ever wrote, many, many years ago, was on bootstrapping 3D n equals 8. And so what has changed in all those years? So the main thing which changed in our recent paper is that we showed how to impose both localization constraints, including the one that involved an integral, because that was much harder. So in an earlier paper that we had back in 2019, we only imposed one of the localization constraints, which was the one that didn't involve an integral, and that gave us the island shown here. So this is an island in terms of the OP coefficients of these semi-short multiplets, and recall that you get islands automatically. You don't have to put in any assumptions to get islands in this theory. And so this island was already pretty small in the 2019 paper, as you see from these axes. But once you put in the second integrated constraint, the one involving the mixed mass derivatives, then the island shrinks by a factor of 100, and it becomes this little red region here. And so you see kind of the power of imposing localization. We get a super tiny island. Okay, so that island is so small that we can actually start to learn about 1 over n corrections, something we were not able to do in the n equals 4 case. So in these plots, on the x-axis, we're focusing on the large n regime because we want to study 1 over n corrections. And the y-axis is the upper and lower bounds, i.e. these rigorous islands on OP coefficients of these semi-short operators. And so we can look at two different theories, k equals 1 or k equals 2. The reason why there's two black dots is that you have the ABJ theory as well as the ABJM. And so kind of the exciting result we see here is that when you compare this to the analytic large N expansion, you see that after including the d to the 6 r to the 4 correction, so you start with green, then you go to red, then you go to blue. So after including this final correction, it lands you right exactly in our rigorous island. So this shows that we're really sensitive to the d to the 6 r to the 4 correction, and we exactly match it, which was very nice because these large N calculations are very hard, and it shows we didn't make any mistakes. Question? No, it has maximal supersymmetry. Yeah. Yeah, there's also the n equals 6 theory, which has slightly less. And in that case, k could be anything, but here we're just focusing on the maximally supersymmetric case. Yeah, so right now the bootstrap is sensitive to all the protected M theory corrections, which means all the way up to d to the 6 r to the 4.
So just to be sure, you say that when you include this CT to the -7/3 correction, it falls into the allowed range, but
Yes.
I mean, but you could have imagined the next correction just numerically somehow.
That is the very next slide. Yeah, so indeed, if our islands were even smaller, then you wouldn't expect this blue to lie within the allowed region, because you would expect that there would be more 1/n corrections, and they would be needed in order to get within that island. And so the fact that it's in the region is a success in some sense, because it means that we're on the right track, but we want the island to be so small that we're actually outside the region.
I'm just trying to say that a priori it's not obvious why it should lie in this island in the first place, just because, I mean, the next door correction, it differs by some fraction of power, which is not.
Yeah, I mean, so I mean, it depends on how convergent the large N expansion is. I mean, in principle, we could always look at a big enough value of N such that we could maybe trust that these 1/n corrections that we're ignoring are so small that they wouldn't matter. Although, of course, it could always be that, so I mean, it's a game of kind of increasing the value of N such that you're not sensitive to the next corrections. Anyways, so kind of related to Shai's question, we want islands that are so small that actually we are sensitive to the next correction, which is beyond d to the 6 r to the 4. And indeed, we have those small islands for this other CFD data, which is this A2 coefficient. So in this case, you find that even after including all the known corrections up to d to the 6 r to the 4, you see this blue line is outside the allowed region, which means that we are sensitive to the next 1/n correction because we need that correction in order to, be in the allowed region. And so what we do in this plot on the right-hand side is that we plot the difference between the analytic 1/n correction, known to order CT to the -7/3, and the island. And we do this for many different values of N, and we do this log-log plot on the difference between those results. And so here we want to see if the next correction has a power 23/9 or not. Because from M theory, we expect that the next correction would be d to the 8 r to the 4 unless that correction happens to be 0. And so by doing this log-log plot, we find that the slope, which is the power of CT, is minus 22.3 plus or minus 0.52 over 9, which is consistent with 23/9. And so this is kind of the first success of the numerical bootstrap, learning about unprotected string theory, the fact that our island is so small that we were able to accurately predict the next correction in 1/n, which matches the expectation from M theory. And so it also shows that this d to the 8 r to the 4 contribution to this specific CFD data is non-zero.
Can you remind me what is the CT scaling of the one loop with the r to the 4th vertex?
That is 24/9. Slightly higher. But depending on how much you trust this plot, excluded. And so we have a similar plot also for k equals 2. So here we're just showing k equals 1. Okay, so now let's look at the coefficient. So now let's just assume the next correction is 23/9 as we expect, and now we can do a fit to find that coefficient. And so we do it for k equals 1 as well as k equals 2. And so we get these numbers. It's like roughly 8 times 10 to the 4 and roughly 4 times 10 to the 4. And there's actually a prediction for the ratio between these two numbers, because this d to the 8 r to the 4 is a contact term if you think about it in terms of Witten diagram contributions to this correlator or to the CFD data. And this contact term from dimensional analysis, based on the fact that the volume is 84 across the 7 mod zk, we expect that it should scale with k like k to the minus 14/9, which means that from M theory, we expect that the ratio of this coefficient should go like 2 to the 14/9, which is 2.9. And indeed, that ratio is consistent with the numbers we get, which I think is very cool. Now, of course, these numbers are still very approximate. So, you know, I mean, I wouldn't put my money on maybe like the third digit here. But the fact that it's even like in the ballpark of 2.9, in fact consistent, I think is quite impressive. Because after all, the ratio could have been 1 billion. You know, there's no reason why it had to be around 3.
Just to be sure, it is slightly less than 2, right? So it's 50% error.
Well, no, but I mean, okay, but we have these error bars. I mean, it depends how you interpret the error bars. If you do the plus here and you do the minus there, then it's consistent. But of course, I mean, look, you know, this is like a first attempt at this. I mean, the point is that like the fact that the magnitude is even the same is impressive, because like the magnitude really could have been anything. It's like it's not like it was obvious that it had to, you know, be this ratio. So I would say this is kind of like the first real evidence we have that we are probing unprotected string/M theory using the numerical bootstrap. So after all these years, we finally made contact with something new.
Let me try to understand the conclusion. Are you determining a term that survives in the flat space limit or not?
Okay, so what we have computed is the d to the 8 r to the 4 correction to a specific CFD data. If we want to determine the d to the 8 r to the 4 correction to the full correlator, recall from a previous slide, we need 4 constraints, because there's 4 unknown coefficients at order d to the 8 r to the 4. So we have 2 constraints analytically from localization. We now have a 3rd constraint from this numerical thing we just computed. We would need 1 further constraint in order to fix the full correlator and then take the flat space limit. So we're not there yet, but we're close. So what we're hoping is that, I mean, okay, so I'll discuss this in the conclusion slide. So maybe we should just go to the conclusion. So what have we found so far? So we found that bounds from combining bootstrap with localization give a non-perturbative solution to holographic CFTs, which works at finite n coupling. So non-perturbative in everything. So for n equals 4 super Mills, the evidence we have for this is by comparing upper bounds to predictions from weak and strong coupling. So there it's a bit of a conjecture, because in principle, just an upper bound. For ABGM, the evidence is much stronger because we have rigorous upper and lower bounds, i.e. islands, similar to what people have for the icing model. And these islands match the large n prediction all the way up to d to the 6 r to the 4. And in fact, they even give predictions beyond d to the 6 r to the 4, which match other expectations from M theory. So like not only are we solving these holographic CFTs, thus solving non-perturbative string and M theory, but we're actually learning new things about string and M theory at long last. Okay, so of course, in the future, the most obvious thing we would like to get is more accurate bounds. Because, you know, as I was just discussing with Shai a moment ago, the goal is that if we can get one more, semi-short OP coefficient in ABJM, if we can compute its d to the 8 r to the 4 correction, then that would be sufficient to get the full correlator at d to the 8 r to the 4, and then take the flat space limit, and then we would have the M theory S matrix at d to the 8 r to the 4, and we could check conjectures by various people, I think perhaps Nathan, that this term might vanish or not. I suspect it probably doesn't vanish, but we don't know for sure yet.
So just to clarify the interpretation of what you're calling d8 r to the 4, it sounds like what you're saying that that term you're determining, let's say, the mailing amplitude isn't literally the d8 r to the 4 term in effective Lagrangian of the M theory. Right?
Yeah, it's not literally that, because when you compact phi Tadius 4 across the 7, I mean, there could be other terms that contribute at the same order in one of our ends.
So what are the other? So the other terms are the lower order terms that are already known, or?
Probably, yeah, because plus that, you know, yeah, I would
yeah,
guess.
I guess that's what we expect. So
yeah.
In principle, if you actually knew the explicit Lagrangian, you could a priori compute that, even if you are ignorant about the actual d8 r to the 4.
Yeah, so in principle, if you were very powerful, you could do the dimensional reduction, compute all the contributions other than d to the 8 r to the 4, and then compare that against our constraints, and then you would probably know d to the 8 r to the 4. But I don't think anyone has ever managed to do a dimensional reduction to that level. But it'd be great if someone could. Anyways, so the hope is just to get more accurate bounds in order to fix this other CFT data and then get the full d to the 8 r to the 4. And so there's various ways we hope to do that. So one way is by considering more localization constraints. Because so far we've considered the constraints but taking mass derivatives. But there's also constraints from considering the squashed sphere. So when you consider this round sphere, you could ask the question, what is the most general geometry that you could compute a free energy which still preserves enough supersymmetry such that you can do localization? And so this question was answered, roughly 10 years ago in the various dimensions. And the answer basically is that there's only one geometry which is more general than the round sphere, which is what's called the squashed sphere. And this geometry is parameterized by just one variable called b. And so you could take derivatives of this b and then go back to the round sphere, and this b couples to the stress tensor multiplet, just like the mass. And so this should also give integrated constraints of the stress tensor multiplet. Now, in the case of 4D n equals 4, in a paper that should hopefully be out soon, we have proven that there are no new constraints for the 4-point function. So there might be new integrated constraints for higher point functions in n equals 4 by taking derivatives of b, but at least for the 4-point function, alas, there are no new constraints. But in the case of 3D n equals 8, we are still hopeful that there might be new constraints from taking derivatives of the squash sphere. Our intuition basically is that localization in 3D requires less supersymmetry than localization in 4D. And so that might be why there would be more independent constraints. And so that's one thing we would like to do to improve the numerical bootstrap. Even if we can't find new constraints due to localization, another way we could improve it is to do mixed correlators with other low dimension operators. Because one lesson we learned from the icing model is that it is good to do mixed correlators with all the operators that have low twist. And so far we've just considered the stress tensor itself, which had this, dimension 1 in 3D or dimension 2 in 4D. But there's another low-lying operator, which is the Konishi multiplet. Because we know at weak coupling that also has roughly dimension 2 in 4D. And then there's some analogous operators in 3D. And so it would be interesting to do mixed correlators with those long multiplets. The main difficulty in that case is just that there's many crossing equations. Because basically you're going to have a crossing equation for every single operator that appears in that supermultiplet, because the OP coefficients are not related by supersymmetry anymore. And so this means you're going to have some huge crossing system, but due to all the wonderful advances by the Bootstrap collaboration, I think it should hopefully be possible to implement that. And then maybe we can get better bounds in both 4D and 3D. So another thing I'd like to emphasize is that this method of combining supersymmetric localization with Bootstrap in order to numerically solve theories is quite general. So because it applies basically to any context in which you have localization. So in particular, that applies to 3D n equals 2 theories, 4D n equals 2 theories, or 5D n equals 1 theories, as long as you can write down a Lagrangian. And so I've spoken about the simplest cases, which are the ones with maximal supersymmetry, but we've already had some results on some other cases with less supersymmetry. So for instance, there's a certain 4D n equals 2 gauge theory first proposed by Ashok Sen back in the 90s, which is dual to some holographic setup which involves flavor brains. And so I had some work with Connor and Pietro, and in the last couple of years, we were also computing integrated constraints and studying the large n limit. Although we haven't done any numerical bootstrap work on that yet. So that's only been analytic large n. Also, if you take ABGM theory, so kind of related to something Nathan pointed out, there's a more general class of ABGM theories with the supersymmetry slightly smaller, it's n equals 6. And now k can be anything you want, and the difference between the gauge groups can also be anything you want. And so you could also numerically bootstrap this and put in localization constraints. And so we did a first attempt at this with Silviu and Damon and Max back in 2020. But in that case, we didn't put in integrated constraints. We only put in the localization constraint that we knew exactly in terms of the OP coefficient, because we didn't know how to do integrated constraints back then. Question?
So the bootstrap you have considered just for the 4-point function BPS operators, a particular BPS operator, and do you actually, how tight can you hope to get these bounds to be, even if you have put in all the localization constraints?
I mean, who knows? Look, for ABGM, it's pretty encouraging because the islands we're getting are pretty tiny, and they're already sensitive, to all these like higher one-over-n corrections. So I would say the results so far are encouraging. And also, we know from the icing model that just by bootstrapping like all the low-dimension operators, it seems like you get an island which is incredibly small. I mean, in that case, they get how many digits? I don't know, like 15 or something. You don't have to say it. It's fine. Okay, the point is that for the icing model, just by computing a few correlators, they're able to get, like, say, 15 digits.
Well, there seems to be expectation now that you need to include more correlators.
Yeah, but that's if you want to go beyond 15 digits. Like, if we could get 15 digits, I would be happy. I think 15 digits would probably be enough to certainly fix the d to the 8 out of the 4 and probably even fix higher corrections. And maybe Ning will have some predictions for the exact answer.
But there is a logical possibility that you will never fix the 8 out of 4 by this correlator alone.
Okay, but we're very close, though. I mean, we've already fixed the contribution to one OP coefficient. So, it's like, look, if we didn't have the results I just showed you, then maybe I would have been pessimistic. But considering that we've already correctly fixed, the d to the 8 out of the 4 contribution to one CFD data numerically, I think that it shouldn't be too much harder just to get one more CFD datum, and that's all we need. So, I mean, we don't need 15 digits. Probably just a few more would be sufficient, maybe even one. Anyways, so it would also be nice to generalize to this more general class of ABGM, because this family of theories is very fun in that depending on how you change the parameters, you can describe every known theory of quantum gravity. Because you have M theory when n is large and k is finite. You have type 2a when both n and k are both large. And you even have higher spin gravity when the difference between the gauge groups is big. And so by changing these parameters and inputting all these constraints, you can in principle, travel between all the different theories of quantum gravity that people care about. As long as you want dynamical gravitons. I can't help you if you want JT gravity. Okay, so what is the long-term goal of this program? So the short-term goal is to compute these higher derivative corrections, for which I think we're very close, certainly in the case of ABGM. Kind of a grander goal is that if we could get, say, 20 more digits or 30 digits or whatever, and if we could do this not just for the lowest lying operators, but for higher operators, so like unprotected scaling dimensions, say the lowest 10, and if we could compute these as a function of n and the coupling, then we could make contact to black holes. The reason why is that in holography, we expect that black hole states correspond to high twist unprotected operators, because these are operators with very big energies. And if the energy scales like c, then we expect them to be black holes. And so in particular, the idea is that you're scattering gravitons and black holes are appearing. And so in the future, if we can track the statistics of these operators as a function of n and coupling, then hopefully we can see that as we go to the strong coupling regime, these statistics should start matching the expectation for a gravity-like theory, as opposed to at weak coupling where they presumably shouldn't. So this is kind of like the long-term goal of the program, and this should motivate people to keep improving the bootstrap so we can get more and more accuracy. Because this is an example of a bootstrap where we will endlessly gain by getting more digits. So like it's not just like we're getting more digits that we can write on Wikipedia that we have like 50 digits, for the IC model. As wonderful as it is, in this theory, the more digits we get, we will actually be learning new physics. Okay, so that's it.
Questions for Shai?
Hi, thanks for the talk. I want to hear more about the extrapolation in terms of the lambda. So
sure.
Yeah, so I think you, in the leading order, you get something like a 1 over lambda convergence, right?
Okay, so you want to go back to this plot where we show how things depend on lambda? Here, this plot.
Yeah, so the leading convergence is 1 over lambda.
Yeah, so yeah, that's kind of like the usual intuition from the bootstrap. I mean, going back to Rosselli's paper 10 years ago.
So is this general for any bootstrap, or this is specific for this situation?
No idea. I don't think there's anything rigorous known about this. I mean, I think people in practice used this assumption in different contexts in the bootstrap, and it seemed to give a reasonable result.
Yeah, I think I've seen some other studies also showing the 1 over lambda convergence.
I think it's just because it's the simplest thing. Yeah, but like I don't think there's any proof.
Lambda is something like the number of the bases is square of lambda.
Yeah, so if you're doing some kind of Taylor expansion around the crossing symmetric point, it's like the number of terms you keep in that expansion.
Okay, I see. Thanks.
Actually, I wanted to just follow up on that. Why is it analytic in 1 over lambda? Why can't you have 1 over square root lambda?
I don't know. Yeah, I mean, all I can say is that this is what seemed to work in many different contexts. But yeah, I mean, it would be nice to know this, like some general expectation.
Paul told me that for some 4D n equals 2 stuff they did, it was more like 1 over square root lambda.
Oh, yeah, could be. Yeah, it could be that at different theories, it changes.
Thanks for that. So in the case of n equals to 4 super young means, did you try to extract extremal spectrum at these upper bounds? Like, does it match other stuff that are known?
Okay. So that's an excellent question. Basically, our results are not yet accurate enough to get a good spectrum. And so the most salient aspect of that is that if we were sensitive to the second lowest operator, so the operator above the Konishi, if we were sensitive to that operator, then we could have imposed that there was, say, only 2 relevant operators, which would have been, say, the Konishi and the double trace, and then we would have gotten an island. Just like in the icing model, you impose there's only, 1 relevant operator, and then you get an island. And so if we would have been sensitive to the fact, we would have gotten an island. Unfortunately, we are not yet sensitive to the second lowest operator, and that's why we do not yet get an island after attempting to put that assumption in. And so one of the goals is that by perhaps doing mixed correlators with this Konishi, our bounds will get more accurate, such that we will be sensitive to at least the second lowest operator, and then we will be able to get an island, and maybe at that point we'll be able to get even more operators. Yeah, but basically the answer is that it's not accurate yet.
Thanks.
I mean, I have some intuition of why that might be the case, which is that for these these integrated constraints, you could check, for instance, in the free theory, where you know everything, like what percentage of the constraint is being contributed by what operators. And so you can check that like the lowest operator, like the spin zero lowest operator, is contributing like 85% of the constraint, whereas all the other operators are contributing 15%, which is why you might expect that you would have less accurate results for these other operators. But in principle, I mean, but numerical bootstrap should in principle be sensitive to everything. So.
What can you say, so about this input for Subramus result, what can you say about the comparison to the Verceau-Shapiro amplitude?
Okay, so that's an excellent question. The best comparison could be done in Frank's work, because in that work, they're focusing on the planar limit, and they're doing it for every value of lambda. And indeed, if I understand their work correctly, they do accurately match Fernando and Tobias's predictions for the OP coefficient.
Sorry, what accurately match?
Well, okay, so in their paper, they do a numerical bootstrap where they input the scaling dimensions and they read off the OP coefficients. It's a function of lambda in the planar limit. And then Fernando and Tobias and Joao had this prediction for what those OP coefficients should be, say for the Konishi, and they match that, in the large lambda regime. And so because that's the regime where you could compare. Our results, I mean, in principle, they're finite n and finite lambda. And so in principle, if you went to big enough lambda and big enough coupling, you should be able to compare it to that regime. But we're only looking at the lowest dimension operator. And the lowest dimension operator in the strong coupling regime is not the Konishi. I mean, the Konishi is going like lambda to the quarter. And so that's why we're just not looking at the kind of data that one extracts from this ADS-Verceau-Shapiro.
Are there any further questions? Well, if not, let's thank Shai.